In Chapter 8, we are finally going to get to describe chemical bonds, how bonds form. We're going to come up with a very simple model to help us predict how many bonds get formed. And in this first talk on Section 1, we're going to define different types of chemical bonds and introduce a very simple rule to help us predict bonds. So the entire basis of bonding, first formulated by G.N. Lewis, who is a professor at University of California at Berkeley in the early part of the 20th century, published a very influential book called The Atom and the Molecule. And it's hard to put in perspective the insight that Lewis had here, because this is some 20 years before quantum mechanics was really formulated and worked out in a way that we could predict electron configurations. But based on observations, Lewis came to the conclusion that it's all about the electrons. Bonding is all about the electrons. If we focus on valence electrons in particular, we can work out some of the principles and guidelines to help us predict types of bonds. So let's look at the types of bonding that we see in chemistry and define them. There's really only three main types of bonding in chemistry, and we're going to focus mostly on the first two that I define here, but I want to tell you about the third one because it is an important type. The first type that we're going to look at is ionic bonding. You can think of an ionic bond as the bond formed by a complete transfer of one or more electrons and the subsequent electrostatic attraction of the ions formed. It's literally just the attraction between a positive and a negative charge. It has no directionality to it. A positive charge would be attracted in any direction to a negative charge, and that leads to some of the characteristic properties of substances that are held together by ionic bonding. The second type is covalent bonding. You can think of this, and this is a rough idea, as bonds being formed by sharing one or more pairs of electrons between a pair of atoms. Notice that the sharing is almost exclusively in terms of pairs of electrons rather than individual electrons. And thirdly, the type of bonding that we're not going to spend a whole lot of time on, but I just want to give you a very brief introduction to, is metallic bonding. This is the sort of bonding that holds metals together. And in it, it's sort of an extension of the idea of covalent bonding. Rather than sharing valence electrons between a pair of atoms, the valence electrons of all atoms in the metal are shared by all of the atoms simultaneously. So we think of atoms being embedded in the sea of electrons, and that leads to the characteristic properties of metals, such as very high electrical conductivity, because those valence electrons can move from one side of the entire metal to the other. Very high thermal conductivity, again due to the motion of the electrons. The shiny metallic appearance is due to this sea of valence electrons, etc. That's about as much as we're going to cover on metallic bonding, but we are going to go in considerable more depth to try to understand better ionic bonding and covalent bonding. To do that, let's look at something that G.N. Lewis introduced called Lewis symbols. This is a way of keeping track of the all-important valence electrons in order to predict things about bonding. So here's the rules for drawing a Lewis symbol. Now, a Lewis symbol is different than a Lewis structure. If you've encountered Lewis structures, those are two different phrases. They're very closely related, but they're different. So a Lewis symbol shows all of the valence electrons around an individual atomic species. It could be an ion, it could be a neutral atom. In order to show all of the valence electrons, that means you need to know how many valence electrons an element has. That's very easy to do if you have a periodic table. If the element is in one of the A groups on the periodic table, that's the tall columns, the number of valence electrons is simply the number of the column. Count the columns over, however many columns over you go from left to right, that's the number of valence electrons, and I'll show you some examples. Then you place the electrons in one of four regions around the elemental symbol, meaning the top, the bottom, the left, the right. Just restrict it to those four regions. Place one dot in each region before placing two dots in any region. And the reason behind this is sort of a generalized version of Hund's rule. The electrons like to spread out as much as possible so that they can have their spins point in the same direction. So let's just do a few examples of Lewis symbols. So to do this, for oxygen, I look up on my periodic table. I see that oxygen is in group 6A. That means it has 6 valence electrons. So I start, it doesn't matter which side, which region you start, left, top, bottom, right, it does not matter. But I'm going to start on the left-hand side and draw a dot. There's 1, 2, 2, 3, I lost my first dot, 4, 5, 6. There's my lowest symbol. That's it. That's all there is to it. For carbon, carbon's in group 4. 1, 2, 3, 4. There's the lowest symbol. Fluorine is in group 7, so it has 7 valence electrons. Remember, we're only showing valence electrons, not the total number of electrons. 1, 2, 3, 4, 5, 6, 7. There's the Lewis symbol. Now, one of the nice things about Lewis symbols that we can use it to predict how many bonds an element will tend to form. So oxygen, for example, has 2 unpaired dots. We can use that to predict that it will form 2 bonds, typically, like it does in water. Carbon, 4 unpaired. It will typically form 4 bonds. And fluorine, with 1 unpaired, will typically form 1 bond. So that's a prediction that we can make just based on Lewis symbols directly. The book has a table, table 8.1, showing you even more Lewis symbols. Notice that, for example, elements in the same group have the same looking sort of Lewis symbol, obviously a different elemental symbol, but the same number of dots. So 5A, nitrogen has 5 valence electrons, as does phosphorus, so it has the same sort of arrangement. Let me just point out, for example, they did a slightly different drawing of oxygen Lewis structure than Lewis symbol than I did. The only thing that matters in the Lewis symbol is how many of the 4 regions have pairs of dots, how many have single dots. It doesn't matter where the single dots appear. So in their oxygen, they have in the top and the bottom. Mine had it on the top and the right or something. It doesn't matter, okay? All that matters is that 2 of the regions have 2 dots, 2 of the regions have single dots. That's as much as we get out of Lewis symbols. Now the reason we can predict the number of bonds from a Lewis symbol has to do with something developed by G.N. Lewis called the octet rule that we're going to use to help predict bonds. It's a rule of thumb based on empirical evidence. It's not calculated or derived from anything, but it's just simple practice that in general, atoms tend to gain, lose, or share electrons in such a way as to end up with 8 valence electrons in their immediate vicinity, hence the octet rule. This has to do with the special stability of 8 electrons associated with the valence electron configuration of noble gases. That's a particularly energetically stable arrangement. Now, although Lewis is often accused of stating this octet rule like this, in fact, what Lewis said is that atoms tend to gain, share, or lose electrons so as to acquire the nearest noble gas configuration. It's not always an octet. So, for example, hydrogen never ever ends up with 8 electrons. But in order to achieve the nearest noble gas configuration, it wants 2 valence electrons, so that it looks like helium, which is the nearest noble gas, which does not have 8 valence electrons. And let me just emphasize, this rule is a summary of the usual tendency. It's not a hard and fast rule that is never ever broken, but it is a very useful rule of thumb, and we're going to use it regularly.